Copyright Stanford University, all rights reserved.
Okay, good afternoon, everyone. Welcome to the IEEE seminar. It's my pleasure to introduce Adrien Depeursinge, who's a postdoc in my group. And he's from Switzerland and soon to be faculty. He's got some applications out. Don't have news to announce yet. But he's doing exciting work in quantitative texture feature analysis, which he will be talking about. It has a broad variety of applications, not only in radiology, but also pathology and other imaging domains. And look forward to his presentation. Oh, yes, at the end. Don't anyone leave at the end, because there's a cake cutting ceremony in honor of a recent PhD graduate, Jessica. So hang around at the end of the talk today. Thanks.
So good afternoon, everyone. So I try not to be too long, so we have some time for champagne at the end. So thank you all for coming. I would also like to thank the IEEE faculty for giving me this opportunity to present my work in this seminar series. So today I will talk about texture-based computational models of biomedical tissue in radiological images. And so this is the agenda of my talk. I will start with motivating why we need computational models for leveraging modern radiological data. And I will also go through the state of the art to point out some of the limitations that we will try to address in this work by building highly adaptive texture models. And we will evaluate these texture models on 2D and 3D non-medical textures first. And then we will go through two medical applications. First one will be to predict the risk of lung tumor recurrence in CT. And the second one will be to predict semantic terms describing liver lesions in CT. And I will finish with conclusions and some perspectives of this work. So let me start my talk by stating that radiology data meets all the criteria for being big data. First, because it's literally big. So there is a recent report from the European Commission that estimates that medical images of all kinds are amounting up to 30% of the worldwide data storage. So it's really big. And also it's quickly increasing with a growth that follows more or less more slow while doubling every 2 years. It's also very complex data because there is typically multimodal data, multidimensional. So here on this small video, you have here whole body MRI with two different sequences. So first, it's a lot of data to go through, to analyze manually. And also, it's not very easy to understand what exactly is modeled by these two different sequences. So human analysis of this data is very time consuming, and it's okay to do it for maybe one data set, but for a large cohort of patients, it's very difficult. But if we are able to build computational models to leverage this data in an automatic fashion, there is a tremendous potential for biomedical discovery. For example, to reveal disease phenotypes with a very unprecedented accuracy, like using a very large cohort of patients. And there will be direct benefits to the patient, while we could build and learn very specific imaging biomarkers that could maybe surrogate or maybe even surpass invasive biopsy, current biopsy biomarkers, or even more complex and costly molecular assays. So there is a new emerging field, the emerging research field of radiomics, which aims at automating those processes of analyzing this large cohort of patients. It aims at high throughput extraction of quantitative image features with the intent of creating mineable databases from radiological images. So it aims at modeling all the different processes for analyzing this data, starting from really image acquisition, reconstruction, storage. Then as soon as we have these images, we want to extract a region of interest from this data, such as, for example, here, a long tumor. And from these regions of interest, we want to extract descriptors, so typically quantitative image features that we will maybe link to a prognosis or a diagnosis using machine learning. So for instance, we can tell maybe that this tumor is actually malignant, but it will respond well to a given treatment. So in this work, we will focus on the two last steps. So as soon as we have this object of interest, how can we really describe it and extract quantitative features to then relate to one class or one disease outcome here using machine learning methods. So what is image feature extraction? Well, it's all about how to leverage, best leverage image content. And there are mainly two approaches in the literature to do that. The first one is to use control vocabulary and semantic features to describe the content of the images with human descriptions. So for instance, if you want to describe the contour of these lesions, we can say it's circumscribed or microlobulated. So those features are easy to interpret because they're directly in human language. And also they're often disease specific, which means that they aim at directly modeling a feature that will be useful for predicting the outcome or the diagnosis. So two different radiologists may say different things when they see these images, so that they have a low reproducibility. And especially if you think in 3D, it starts to be very difficult to describe accurately a 3D shape. And also it's low throughput because it takes a lot of time to really go through all the images and extract those features. So if we want to analyze huge amounts of data, that will be very difficult. So there is another approach, which is to build quantitative features. So really to use computerized image analysis to extract those features. And those could be like intensity, shape, or texture. And the good thing with those is that they're very reproducible. If you give the same image, they will always give the same feature value. And it's very high throughput because we are only limited by the computational power that we have at our disposal to analyze a large cohort of patients. The drawback of those is that they are difficult to interpret. They don't directly correspond to something that is also specific, so they're unspecific. They're not directly modeling the disease outcome or diagnosis. So in this work, we'll focus mainly on computerized analysis of texture, because texture is something that is very difficult to describe with semantic terms. So if you want to describe, for instance, this lesion in a breast, it's very difficult. You can say maybe that this region here is more homogeneous and this one is more heterogeneous, but it's difficult to go beyond those very simple descriptions. So we think that there is tremendous potential of using computational methods for texture. And also, so other computerized measures like intensity and shape are often of limited use to characterize biomedical tissue properties. So as an example, if you want to discriminate between those 5 types of lung tissue, maybe using intensity you can discriminate between some of them, but it's definitely about texture here that we can separate those patterns. So 2D and 3D texture analysis can quantify micro and macro structures in biomedical images. And as a few examples here of the geometries of those texture, they can be radial, such as like nodules, or linear, like vessel or bronchus, or even surfaces, like brain gerification, or even arborescent, if you think of a vascular tree and so on. So there are mainly two properties that are very important to characterize texture in images. The first one is a change in scale. So you can see that the only change between these two textures is a zooming effect. And the other property is the direction. So here, for example, this texture only has vertical directions, and this has a more heterogeneous distribution of the directions. So most approaches in the literature are leveraging these two properties, such as gray-level co-occurrence matrices, directional filter banks, or wavelets, or histogram of gradient, which is well used in SIFT, for example. But there are many limitations of these approaches, and we will go through some of them now. So most approaches in radiomics are assuming that the properties, the texture properties are homogeneous over the whole lesion. So if you consider here, for instance, a glioblastoma tumor in MRI, it's pretty clear that the texture is very different close to the boundaries, or maybe here, which is maybe a necrosis region, or another region with proliferative cells. So if you average the texture properties over the whole lesion, then you will miss a lot of information. Another limitation is that the texture features are usually non-specific. So for example, if you characterize the spatial frequency along the z-axis, it's very unclear if this will be a good predictor of disease outcome, for example. Another limitation is that most of the approaches have a limited characterization of the direction. So they will typically approximate the angular space using these vertical, horizontal, and diagonal direction. So in 2D, it's maybe still okay to do that. But if you go to 3D using those 13 directions, you start to miss a lot of information. So in this graph, it is the number of missed voxels based on the radius of the neighborhood, so of the window for interpretation. And we can see that in 2D, it's the quadratic relationship, so it's still okay. But in 3D, with neighborhoods bigger than 5 voxels, you really start to miss a lot of information. So this is 10 to the power of 4 here. This is something to keep in mind. And there is another property that is also often neglected in the literature, is that if you only characterize the global distribution of orientation in images, then you are not able, for example, to discriminate between these two patterns. So hope you agree that those two patterns are visually very different. And if you just want to characterize the amount of vertical and horizontal directions, it will be the same for those two patterns here. So what really matters is how these directions intersect together. And so we need to characterize the local organization of image direction. And if we can do it also independently from their local orientation, then we can also discriminate here patterns with random local rotations. So in this work, we will leverage one property that will help for both of these two problems, which is rotation covariance. So rotation covariance consists of a local group steering of the operators. So imagine that we have these two image operators, which this one characterizes, for example, image directions, vertical directions. This one characterizes the orthogonal directions, so let's say horizontal. Then if we can locally align the operators on the structures, such as, for example, maximize the orientation of these operators to maximize its magnitude, and then look at the orthogonal directions, this will normalize all the instances, so align all the instances together to allow a hierarchical categorization of the directions. And I have a small video here to illustrate this process. So imagine you want to discriminate between these two patterns here. So this is a pattern that only contains this cross here, and it's denoted in black in the feature space. And this is a pattern with two bars that evolves and crossing at different points. This is a pattern here denoted with red cycles. And here we compare three approaches. So the first one is using the gray level co-occurrence contrast along the X and Y axis. This is using the operators we were describing before, but without aligning them. And we can see that when we align locally the detectors on the structures, then we're really able to discriminate between these two patterns here. Also, when we start to add random rotations in these two patterns here, then we are still able to discriminate them when we align the local operators, because as we align them locally on the structures, then it doesn't matter how they are locally oriented. So in this work, we would like to propose a novel, highly adaptive texture-based computational model of biomedical tissue that fulfill these properties here. So we want operators that are able to perform a complete coverage of image scale and directions. We want operators that are rotation covariant, so that we can locally align on the structures. We want also operators that are specific, so that can be trained to characterize a given tissue type. And finally, we want also to be able to characterize the local tissue properties and not averaging over whole lesions. So if we are able to do that, we expect that we can really allow for an accurate modeling of the disease phenotypes in radiological images. And if we can run it on really large cohort of patients, then we should be able to enable biomedical discovery and understand new fundamental pathological pathways, for instance. So let's see how we can build those models. So we will heavily rely on one image processing framework, which is the Riesz transform. And because the Riesz transform allows for multi-directional, multi-scale, and rotation covariant image analysis. So let's see how we can do that. So the Riesz transform yields n+1 components. So if we want n+1 image operators, which are defined in the Fourier domain as follows. So please ignore this term here and focus on this part. So here in the Fourier domain, we have the multiplication by the j omega on the numerator. So and this provides directional derivatives. So we have a directional derivative along the x and y axis. And these derivatives are somewhat cancelled by the division by omega here in the denominator. So what remains in the end is that we have only a characterization of the phase. So in 2D, it's the direction. And those directions are defined by the combination of these two derivatives here. So let's see a bit more concretely how these operators look like in the spatial domain. So for instance, with an order, a Riesz filter bank of an order of 1, it's pretty clear that we have here a first order derivative along the x and along the y-axis. So then, if you convolve these operators with an image like this, it will really allow to separate between the vertical and horizontal directions. Then you can increase the order of those filter banks, and then you can have a better characterization of the angular domain. And you can go to any order that's needed for a given application. Then we can have multi-scale versions of those filter banks by combining the Riesz transform with an isotropic multi-resolution framework. And so if we remember the good old wavelet transform, we know that if we choose correctly our filters and our scale progressions, such as, for example, dyadic here, where we double the scales at every iteration, then we're able to have a complete coverage of the frequency domain. There is another property that is useful, which is the steerability. And so steerability means that we can synthesize any orientation of the filters using a linear combination of the basis filters. So those here is a vector containing the basis filter. And this is just a steering matrix. It only depends on the angle that you want to use to orient this guy here. So let's have an example here with the first order. So you can see that if you appropriately choose the coefficients here, which are the cos and sin theta, you can really generate any orientation of this filter here. This is also available for higher order. And so at this point, we realize that we can have a complete coverage of the scales. We can also have complete coverage of the image directions. And with the steerability, we can locally align the filters to have also rotation covariance. But at that point, we still not have specific templates. So those templates are not being any specific to model tissue properties. So we will see now how we can use these filter banks to learn a model that is specific to a given pattern or to a given tissue type. So for this, we will consider that a Riesz filter bank constitutes a dictionary of very basic textures. So this is a Riesz filter bank with an order of 8. So we have 8 order derivatives along the directions, and they're composites here. And then we can build higher level texture models from linear combinations of these patterns here. So let's have an example. Imagine that we want to learn what is the specific model of this pattern here. Then we can find the optimal linear combination of these guys here to create this model. So we will add a little bit of this one, then a little bit of this one. And so if you look here, we can see that the model evolves up to really modeling the essential stitch of this pattern, at least at a given scale. Okay. So the question is then, okay, fine, but how can we define this weight here to find the model that corresponds to this image? And for this, we can use supervised machine learning and using one versus all configuration. So typically, we can express all the instances of this texture, so all small blocks, if you want, in a feature space that is spanned by the response of the basis Riesz template. So really, how much these guys here respond on this input image. And if we express all instances of these textures versus also all others, then we can learn maximal separating hyperplane to find what is the corresponding importance of those patterns to differentiate between this texture and the others. So we can obtain this vector of weights that we can reinject here to learn the pattern. So in this work, we use supervector machine to do so, but we can probably also use other machine learning frameworks. And also, we can do that with multi-scale filter banks, so which means that if we express the texture here in a feature space spanned by the multi-scale Riesz filter bank, then we can really have a multi-scale signature of the tissue. So let's check that everything works as we want. So here we extracted some of the models for 2D synthetic textures. So what we can see is that when there is a change in scales, the model also changes in terms of scale, and the same thing for orientation. And when we had more complex transformation, we also can extract the model at a given scale. So we can conclude that those models capture the specific local properties in terms of image scale and direction. So here we used we computed the models for some long tissue here, and so for those first three, it's not very obvious, but for fibrosis and macronodule, I think it's pretty clear that we have here a fibrosis detector, and here a macronodule detector. For example, we have a very high peak here in the middle, which looks for small localized nodules. So we also extended it to 3D. So we can have here a vertical plane detector or a 3D checkerboard detector, or if we start to wiggle this checkerboard, the signature is also changing here. Okay, so now we have those models, and we will see how we can locally align them to allow for rotation covariance. So we would like to steer these models, and so now that we are able to have this vector of weights, which characterize the model, we can just directly inject it back to the steering equation. And we can see here, so this is the model, and we realize that we can synthesize any orientation of the model just using a linear combination of the basis Riesz templates here. So now to have a rotation covariant model, we can, for each point of the image, rotate it to find its maximum magnitude here. So we will find an angle for each point of the image, and then we can create a magnitude map of the image, and as then quantitative feature, we can just use the energies of the magnitude over the image. So if we do that for each models, then we can have very specific features characterizing the response of a given tissue. So if we have a model of this tissue, it's expected to have very high response when you convolve it with this tissue. So this is the framework. Let's evaluate it here now with different applications. So first, we will use the models to classify 2D and 3D non-medical textures. So we will start with this database, which contains 24 classes of different carpets and rugs. So this is a database that's well used in the literature to compare texture analysis algorithm. It's the Outtext database. And so it contains 24 classes. There are 180 images per class. And those classes are rotated using 9 different rotation angles. And so we are only allowed to train the system with unrotated image only. And then we can test on the rotated instance. So it will really show how the operators are able to deal with rotation. So this is the performance that we get. So this is the classification accuracy for different orders of the Riesz transform. And here we compare 3 different approaches. So the first approach is using just the initial Riesz template. So we do not learn the model and we do not align them locally. And what we see here is that we have a not very good performance, and also the performance decrease when we increase the order of the Riesz transform, because for higher order of the Riesz transform, you have more templates, so you have more features, and those are not helpful for classification. So it really, you're facing the curse of dimensionality, and the performance is decreasing. Another approach that we are comparing here is, here we do not learn the models, but we align locally the templates on the signal to allow for rotation covariance. And we can see that this really allow here a huge boost in terms of classification performance, which highlights the importance of rotation covariance, as I showed in the introduction. Then the third approach in red is when we learn the models. So we learn the model for each of these class here, and then we align them locally to have rotation covariance. And so this allows to boost even a bit more the performance. And even if it looks pretty similar here, this boost is important because this is really for the instances that are most difficult to classify. So it's also an important boost. So we had the best performance for an order of 8 here, which is, so in the literature, it was between 90 and 99 performance. So we are among the top performing one. Now, if we want to look on when the system fails a little bit, so we've seen, so it's a pity that it's actually cut here, but so this is the confusion matrix here. And we can see that we have the errors are occurring for the textures that are most stochastic, actually. And this is because for very stochastic texture, it's not very easy to learn a clear model or a clear signature. And so we have a limited specificity. But so maybe we can differentiate between these textures and the rest of them because the absence of a clear model. But then when we want to discriminate among them, it's more difficult. Okay, so let's see now how we can classify 3D textures. So we use here a database, this database, which contains 15 classes, those classes here. And so they are defined in the Fourier domain. So there are typically synthetic textures. We have 10 images per class. And there is one normal version of the database, and also several versions with various textual alterations, such as random rotation, noise, smoothing, or subsampling. So here we train only with the normal version of the database, and we see how the operators performs with the altered version of the database. So we use SVM and the Lim-Voinart cross-validation. And these are the results. So we have here the accuracy for various alteration of the textures. So this is the mean for all of them. And we compare here 3 approaches. The first one is using 3D GLCMs. So we optimize here gray level co-occurrence matrices in terms of displacement and directions, and also number of gray levels. And this is the best results we could get in red. And we compare only two approaches using the Riesz transform. So in this application, we do not learn the models. We just try with the basis Riesz component, and also when we align the component. So in blue here, it's the basis Riesz component, and in yellow is when we align the components. So what we can observe is, obviously, when we rotate the instances, it's very important to have rotation covariance. But actually, it helps for all actually alterations. So there is a substantial gain here for all applications. So once more, it highlights the importance of rotation covariance. Okay, so now that we are a bit convinced that the models can model natural texture, we want to use those models to, yeah, if we can get more contrast, it could be better. So let's now use these models to, for medical applications and modeling biomedical texture. Yeah, so we would like to use the models here for the prediction of, to predict the risk of lung tumor recurrence in CT. So it is known in the literature that the density of the lung nodules is an indicator of cancer aggressiveness. So we would like to address the following question here. Can we predict the risk of tumor recurrence from texture appearance of the nodules in CT? So this is a CT image that is very well zoomed, and this is the delineation of the nodules, and with different components. So we asked an experienced radiologist to delineate so this is the ground glass component of the nodules, and those are the solid parts. So I guess it's not very easy to see on that image, but okay. So to address this question, we have a data set of 91 patients with adenocarcinoma. And from these 91 patients, 17 of them had a tumor recurrence. So we have, at that point, an image, which is just before surgery. Then the patient had the tumor removed, and they've been followed for 7 years. And during these first 7 years, 17 patients had a recurrence during that time. And the others, some of them left the study, and some of them were still there till the end of the study. So it's typically right-censored data that we have here. So what we wanted to do is to learn two texture models. One texture model of the GGO component, the ground glass component, and one model of the solid component. And we would like to use these models as features to predict the risk of tumor recurrence. So we also used other features, such as gray level intensities here in the extended log window, and also the age of the patient and the sex of the patient. As machine learning approaches, we compared survival SVMs and the Cox-Lasso, the GLMNet models with L1 penalty to predict the risk of tumor recurrence. As instance in our feature space, we use only the solid regions. So what we are doing here, we are learning the models on solid and GGO, and then we look at the magnitude of those models, but only in the solid components. Then we use a tenfold cross-validation, which is stratified and split by patients. And we will repeat this cross-validation 20 times to assess the performance. At the performance measure, we use the concordance index. So concordance index is similar to the area under the ROC curve, but for outcomes that are non-categorical. So these are preliminary results that we have here. So, so a C-index of 0.5 will correspond to a random prediction. And here, when we use only the gender of the patient, we already have something which is well above random. And this is in accordance with a recent paper that was published in the New England Journal of Medicine, saying that actually women have a really higher risk of having a malignant nodule at the first screening on CT. Then when we include some intensity features like this, here the performance increases a little more. And when we use first texture features, so this is the unaligned Riesz components, we can improve a little more. And when we use the response of the steer model, so for solid and GGO, and when we combine it with the two other feature groups, we can obtain with survival SVMs a performance, which means that for 4 patients over 5, we are able to predict the risk of a tumor recurrence within the 7 years. So that could be pretty useful in clinical routine, where at the time of just before the surgery, you can already tell if there will be a tumor recurrence. So you can closely follow this patient to assess the risk. Okay, I would like to say that this is still preliminary results because we need to assess the statistical significance of those results. And we need also to see how much those performances are sensitive to the accuracy of the annotations here. So what happens if a non-experienced radiologist start to also include some normal tissue here or more of the GGO tissue here? So we still need to assess this before moving one step further to the clinical routine. Okay, so let's have a look here to another medical application. So at that point, we wanted to see if we can use the models to directly predict semantic annotations that radiologists are using to describe liver lesions in CT. So we have several semantic annotations, such as the description of the margin here. So this is poorly defined margin. This is a smooth margin. And also semantic terms describing the inner texture of the lesion. So if we can do that, we can achieve 2 goals. First, we can assist the radiologist with an automatic prediction of semantic terms within the lesion. So it will provide a second opinion to the radiologist. And then if we are able to do automatic prediction of semantic terms in a large cohort of patients, imagine, for example, the whole PACS of the hospital, then we can retrieve liver lesions with similar visual appearance. And so that could be useful as diagnostic aid. So for example, you want to know what's the diagnosis of this lesion here, you will retrieve all the lesions that have the similar semantic terms. And so it can show, so okay, this could be a hemangioma, or it could be also a metastasis, so it can show also the span of diagnosis that could occur. And so when compared to traditional content-based image retrieval, this is useful because it assesses the similarity between the instances based on semantic terms. So if you want, the system really speaks in the language of the radiologist and not using, for example, low-level features such as texture feature or other features. So to assess this task, we have a data set of 74 lesions that are delineated and annotated with semantic terms in CT. So we have a big set of semantic terms. So for instance, we have terms describing the margin, terms describing the inner texture, and also terms describing the overall lesion shape. And in this work, we focus on a subset of 18 terms describing the lesion margin and internal textures. We also assume that those terms are not mutually exclusive, which means that the random prediction is always around 50%. So it's not a multi-class classification problem, but more like a 2-class. So to analyze the visual terms that were on the boundary or in the inner texture, we used blocks on the periphery of the lesion, but also blocks on the inner part of the lesion. So we have overlapping patches like this, and we will perform a random selection of 100 patches per lesion, typically 50 on the boundary and 50 on the inner part. And we will repeat this random selection 5 times to ensure that this doesn't have a high impact on performance. Then we can describe each of these patches here in a feature space that is spanned by the response of the rotation covariance Riesz models for each term. So for each of these terms here, we have learned a specific model. And then we can use a leave one patient out cross-validation with an SVM classifier to assess the performance. And as we have several instances per lesion here, we will just average the decision value of the SVMs from all blocks to have really a decision value at the level of the whole lesion. So these are the results that we got. So here we compare the initial Riesz template, so unaligned Riesz template, versus the learned models that are also locally aligned. And we can see that, so this is the AUC, the area under the rod curve for all 18 terms. And the one with the star denotes the one for which this comparison was statistically significant. And what we can observe is that using the steered models, we have performance that is always higher or close to the best performance. So there are actually 4 terms for which the initial Riesz components are performing better than the steered models. But if we look in more details, for those, the performance is always very close to the best models. Not for this one, but as you can see, it's really close to randoms here, so it's not really meaningful to have this comparison. And so if we compare the global performance for all the terms, it's really highly significant, which again shows the importance of learning the models and aligning them locally to have a rotation covariance. Then we wanted to use these models to really assess how close the 2 visual semantic terms are together. So let's say how close is homogeneous to heterogeneous, for instance. Because if we can do that, we can build a computationally derived ontology, so really relationships between the terms. So to do this, we built the normalized Euclidean distance matrix of all the models. So it's really just the Euclidean distance between those vectors of weight. And this is what you see in this matrix. So it's a symmetric matrix, and on the diagonal, it's all 0 values. And so let's see a few examples here, what we got. So typically, you can observe that between heterogeneous and homogeneous, there is a very high distance. And this is consistent because in terms of texture, those 2 terms are really opposed from each other. Then, again, I hope we can read it well on the screen. But there is here a homogeneous group of terms that are more or less modeling the fact that the margin is not well defined. So we have here irregular margin, lobulated margin, or poorly defined margin. We have another group of terms here that express the fact that the lesion is enhancing, but in a heterogeneous way. But we need to be careful because we also observed some associations that were inconsistent. So we need to keep in mind that the dataset is pretty small, so we have only 72 lesions. But it was just a feasibility to show that we can assess this distance between the terms. That could be useful, for instance, if you want to use a controlled vocabulary, and then to see what this controlled vocabulary means in the context of a given application. So what does this vocabulary mean in the context of liver lesions in CT? Okay, so with that, I would like to go to conclusions and perspectives of this work. So I will first recall all the objectives that we set at the beginning of the talk. So we wanted to build highly adaptive texture-based models of biomedical tissue, which has the following properties. So we wanted to have a complete coverage of image scale and directions, also operators that are rotation covariant to allow them to be aligned on the patterns. And these 2 first properties were enabled using multi-resolution framework and also steerability. Then we wanted models that are specific, that are really modeling a given tissue type and can be trained for that. And for this, we used model learning here. We wanted also not to average the tissue properties over the lesions, so to have a local characterization of the tissue properties. And for this, we use a patch-based analysis or an analysis using different components, for instance, for the lung, where we have analyzed differently the solid part from the GGO part. And so all these properties here could be regrouped into one unique image processing framework, which is the Riesz transform. he also saw that in some cases, using the computerized characterization of the texture can even surpass human appreciation, because we've seen, for example, that using only the texture appearance of the solid parts of the nodule, we were able to predict the risk of survival with a pretty high accuracy. And so if you think of doing this in 3D, it will be even a higher yield, because it's very difficult to appreciate what is the texture in a 3D image. I would like to recall again the importance of rotation covariance to model biomedical structures, because I think that what's most important is not the global distribution of directions in the images, but really how these directions are intersecting. So, for example, in a bronchovascular tree here, or in a spiculated nodule, or even here to characterize reticulation. We've seen that there are several limitations of this work. So, for instance, in terms of model learning, we have seen that we have a limited performance using for stochastic texture. So we need to go further to find ways to discriminate between this very stochastic texture. As we are adding another level of learning in the framework, we need to be very careful with the risk of overfitting. So really to perform well the cross validations and maybe even train the models on a database and test them on another database. Then the rotation covariance comes also with a computational price, because for each pixel or voxel of the image, we need to solve a polynomial of degree n+1 in 2D and this binomial coefficient in 3D. So in 3D, for example, just for an order of 2, you need to ask all of these 6 guys what do they think about the orientation. So that's pretty computationally intensive. Finally, also, we've seen that probably the performance depends on the quality of segmentation, and we need to also keep that in mind, how robust the methods are if we have different quality of annotation. So as perspective for this work, so now I'm really excited to use these models to leverage really large cohort of patients in big data. And we could, for example, build digital tissue atlases. So imagine we can create a prototype of what is idiopathic fibrosis. So what is the texture, prototype textures in the apex of the lung for idiopathic fibrosis, for instance. And so we can create disease phenotypes at the organ level. It also gives the opportunity to establish links between radiological and pathological phenotypes, and also link them to their corresponding genotypes. So imagine we can learn tissue models in a radiological image here in 3D. We can also learn tissue models in the pathological images, and then establish the links between those using also computational methods. And we can also establish the link with their gene expression here. And this is expected to really allow to unveil some fundamental mechanism of disease pathways if we have very large cohorts of patients. So with that, I would like to thank you for your attention. And also the MATLAB code is available for it. So if you want to try it, I'm happy to help you to make it work. And so thank you very much. I'll be glad to take questions. And also, stay here because there will be an apéro for Jessica at the end of the talk. Thanks very much. Yes. Mm-hmm. Mm-hmm.
So, okay, the more and you have
yeah.
omega X, omega Y.
Mm-hmm.
At some point, it might be over.
Mm-hmm.
N equals to, okay, you have 0 combinations where it makes sense.
Mm-hmm.
N equals 8, it seems like.
So so this order really controls the wealth of the filter bank. So of course, so the order really controls the wealth of the filter bank. So of course, if you have a very high order, then you have a lot of you have more features, and there is probably a higher risk of overfitting. but also in terms of, so if you want to learn those models with low orders, you can only learn like ridge or edge detectors. But when you use higher orders, you can really start to learn more complex signatures.
But do you really need the
So n equals to 8 gives n plus 1 components, so 9 components. So I think it's still okay.
I see.
So only 9, yeah. It's n plus 1 in 2D, and it's a binomial coefficient in 3D, so it's a bit more, but it's still okay. So it's not directly those components, because if you take the directional derivatives, there are lots of them are redundant, so you can recombine, and what remains in the end is only n plus 1.
But if you look at the
Mm-hmm.
and then n minus,
Mm-hmm.
combination of different frequencies. Same as splitting the.
Mm-hmm. So in 3D, you have the directional derivatives along x, y, and z. But again, if you recombine them, you have only a limited of them.
So my point is that you really need all of them.
I think so, because when we look at this figure showing the, so I'll go back to it. So for instance, here, so the performance, okay, it's already pretty good with a low number, but if you increase, the performance really increases a little bit. So we should zoom here to see that it's the case. So we didn't get to very high orders, where maybe with overfitting it will start to go down. That's what I'm expecting, but I don't know here.
And what about noise?
Yeah. So my assumption is that if the noise have a very well defined in terms of scales, so a spatial frequency, we can, so as we learn the models in a multi-scale way, we should really give less weight to the scales that are more noisy.
Or from the training?
Yes. Mm-hmm. So when we learn the models here, so then we can have a multi-scale representation of these. And if the noise is not useful, then it should be some way, we should get rid of it. And if it's useful, then it will even receive some weight. Yes? Mm-hmm. That's mm-hmm. So yeah, there is even a steerable version of the Gabor filter. So to me, there might be a yield of doing this, but I think that Gabor filters are also some kind of Gaussian derivatives. So it's very redundant to what we have here. So it's I think there is direct relationships between the Riesz filters and the Gabor filters. Yes.